In the last objective of this section, we're going to look at finding the inverse of a function with a restricted domain. We saw already that some functions are not one-to-one, but we can sometimes restrict the domain of the function so that it is one-to-one. And when we do the restriction, we have to make sure that the range of the function is not changed at all. So for instance, let's consider the graph of y equals x squared. We've already seen earlier that this did not pass the horizontal line test. It is not a one-to-one function. But because the x values to the right of 0 and to the left of 0 are identical, we can actually restrict the domain of this function to the set of x values for which just x is greater than or equal to 0. And when we do that, we get a function that is one-to-one on that restricted domain. If we ignore the left part of that parabola, right to the left part of the vertex, we can restrict it to only be from 0, 0 through 1, 1, 2, 4, and on to the right. So that is the domain and range of that restricted function is from 0 to infinity. And then when we do that restriction, we can actually find the inverse function on that restricted domain. So for instance, if 0, 0 was on the original function, then the inverse function would have the reverse of those, which is also 0, 0. 1, 1 has a reverse of those, which is 1, 1. 2, 4 would go to 4, 2 on the inverse. And so we see that this half parabola that goes to the right of 0 has a inverse function that looks like the square root of x, which we would hopefully make sense to make that connection, right, between x squared and the square root of x. Those are operations that undo each other. So algebraically, we can find the inverse of a restricted domain as follows. We interchange x and y not only in the function, but also in the statements of the restrictions on the variables. So this is the way we would write it. F of x is equal to x squared for x greater than or equal to 0 and y greater than or equal to 0. So when we go through the process of finding the inverse, remember that we let y equal f of x, so we would say y equals x squared for x greater than or equal to 0 and y greater than or equal to 0. Then we have to interchange the x and the y. So we do that in the function to become x equals y squared for y greater than or equal to 0 and x greater than or equal to 0. So we interchange them also in the restriction on x and y. Then we can solve that resulting equation for y to get y is equal to the square root of x. Now normally we would have y is equal to plus or minus the square root of x, right? But because we have restricted the domain and the range, that both the input and the output is positive, we do not need to worry about the negative on the square root of x in this particular case. Here's an example where we want to find the inverse of a function for the given restriction. I have f of x is equal to x plus 1 quantity squared plus 2. Hopefully your mind comes to the fact that this is a parabola that is the basic parabola shifted left 1 and up 2. So that is, it has a vertex at negative 1, 2. If we can restrict its domain to just x is greater than or equal to negative 1, we are then only thinking about the right half of that parabola. To find the inverse then, we're going to write it like this. Let's first replace f of x with y to get y equals x plus 1 squared plus 2. For x is greater than or equal to negative 1, well, what is y greater than or equal to for that parabola? Because 2 is the minimum value of that function, y has to be greater than or equal to 2. And so now we're going to go through and interchange the x and the y's. So I'm going to write it through without doing anything to the x and y's to begin with. And I'm going to go through now and fill in with a different color. So what we get is that x equals quantity y plus 1 squared plus 2 for y greater than or equal to -1 and x greater than or equal to 2. So now at this point, we just need to solve this resulting equation for y. We would do that by subtracting 2 to get x minus 2 equals the quantity y plus 1 all squared. And then we need to take the square root, but because we are ensuring that there is only one output value, we're just going to get the square root of x minus 2 is equal to y plus 1. Therefore, we get that the square root of x minus 2, then minus 1 is equal to y, provided y is greater than or equal to -1 and x is greater than or equal to 2. And so here you kind of see this a little bit clearer, I think, that the domain of the restricted value is x greater than or equal to -1, which is an interval notation, -1 to infinity. The range was from bracket 2 to infinity, right? Everything greater than or equal to 2. And so in our inverse function, which is f inverse of x, which is equal to the square root of x minus 2, then minus 1, we're saying that its domain is x greater than or equal to 2, which is bracket 2 to infinity, and its range is greater than or equal to -1, which is bracket -1 to infinity. So we can see that the domain and range of the function and its inverse interchanged. And if you wanted to think about, well, what does the graph of the square root of x minus 2 minus 1 look like? That is this graph that is a basic square root function shifted right 2 and down 1. So it would have this point at 2, -1, and then it would go up. So we can see that if we put on the line y equals x, that this restricted function and this inverse function are symmetric about the line y equals x. And here's another example. F of x equals the square root of x minus 3. Well, you might think, why do I have to restrict the domain of that? Because the square root function is already only defined when x is greater than or equal to 3, right? Because x minus 3 has to be greater than or equal to 0. And if you think about what the graph of that looks like, it is that basic square root function shifted right 3. So it goes through the point 3, 0, and then up to the right. Well, the range of that function is y is greater than or equal to 0. And so when we are thinking about the restricted domains here, we have to think of this. We say y is equal to the square root of x minus 3 for x greater than or equal to 3 and y greater than or equal to 0. And so now we're going to interchange the x and the y to get x is equal to the square root of y minus 3 for y greater than or equal to 3 and x greater than or equal to 0. So to solve the equation x equals the square root of y minus 3 for y, we need to square each side. This will give us x squared is equal to y minus 3. And now we can add 3 to get x squared plus 3 is equal to y. Well, this is where we see the inverse function. F inverse of x is equal to x squared plus 3. But I can't just say it's equal to x squared plus 3, right? That's an entire parabola. This is why I need the restriction, because if I don't have the restriction, I'm producing an inverse that has more points than what I would reverse on the original function. And so I have to say that the f inverse of x is equal to x squared plus 3 is the inverse, provided that x is greater than or equal to 0 and y is greater than or equal to 3. And so, well, what would that look like? Well, the graph of x squared plus 3 is that basic parabola shifted up 3 units. So we know that it has a vertex at 0, 3. But for the domain to be restricted to just x is greater than or equal to 0, we're only talking about the right half of that parabola. So that part that extends to the right of 3 and goes upward. And now this is why we can see this restriction is needed, because otherwise we have this whole other part to the graph which is not actually included in the inverse function. So the domain of the original function, domain of f, is bracket 3 to infinity. The range is from 0 to infinity. But we can see that the domain of this restricted function is bracket 0 to infinity, and the range is bracket 3 to infinity. Again, to reinforce the fact that the x and y's are interchanged, which means that the domains and range are also interchanged.